Hi, everyone. Hi, Helge. I didn't realize that there are already so many people there.
Hi, Kaspar.
Very good. Hi.
Hi, Fanny.
Hi, Fanny. Hi. Good to see you. Hi. Good. Looking good. Yeah, all right. Good. Yeah, so we wait another 4 minutes. I will try to start as punctual as possible so that we don't build up a delay straight from the start. Okay, yep. And thanks for the slide there. Very good. Good. So, Helge, you're saying everything is now being pushed onto YouTube straight away. Yeah, I see there's a sign at the top, live on YouTube. Okay.
Yes. So I think we need to make sure that we ask everyone for the consent that this is live on YouTube and is also recorded.
Yeah. Okay, good. So maybe I'll ask that question again at 10 to 2, and hopefully that is sufficient. Okay. Yeah, so the recording is happening at the same time, yeah. I mean, it is the same thing effectively, yeah, because we are recording it onto YouTube, isn't it?
I think this is recorded onto YouTube, but I also will press the recording button of Zoom.
Okay.
So essentially, we might have two versions, hopefully one.
Okay, good. Yeah. Better safe than sorry. So yeah, two versions. Good. Okay. Hi, Zbigniew. Yeah, hi. Thanks for joining.
Nice to see you all.
Yeah, thank you.
Thank you for our invitation.
Yeah, of course. Has been a long time.
Yes.
Good. I suppose there will be some latecomers. Should I maybe wait a few minutes beyond 13:50? You give it a few extra minutes for more people to join. Good.
I think that's a good idea.
Yeah, I think so.
Hello, Zbigniew. Also from my side.
Hello. Kaspar, you have a very green garden, as I see.
Yep.
Where are you? In London?
Yes.
Ah, that nice weather. Good climate.
It's actually
in Poland we have only very, very small parts of leaflets till now.
Yeah, but I have to admit what you see behind me is a video.
Ah, okay.
But on the other hand, if even now that I look on the other side of my house, the sun is shining. So it's more or less like what you see in the video here also in London. So not too bad. Not raining today.
Okay.
How about you? Is it raining there over there today, or?
We have several each of kind of rain, snow, sun each day. That currently is the strange situation. Each day we have autumn, winter, and sometimes also sunshine, like on holidays.
Yeah, sounds exciting.
Yes, yes. No. It's like stupid, but nice.
How are the temperatures? How are the temperatures?
At night about 0, at day 10, 23. That it is each day changing.
Okay, good. Yeah.
Such week, of course, such week that I hope that spring will wait for chance.
It will come, I'm sure. Yeah. Good. Okay. So you can see already a screen there. Yeah, welcome. We can see Zbigniew now on the screen. Okay, good. Helge, you were sharing this screen, or Fanny? I don't know. Anyway.
Yes, I was sharing the screen, and I hope now everyone can share the screen who likes to speak.
Yeah. Okay. Good. So I shall try that in a second. Maybe I can do that now. Get things started. Yeah. Give me a second. Oh, I'm sharing already. I'm not sharing yet. Okay. Good. Okay. So I hope you can see my screen.
Yes, we can.
Good. Well, it's maybe a good time to start now. So yeah, thanks for joining our session today, our workshop. My name is Caspar Althöfer. I'm reporting from Queen Mary University of London. I'm the head of the Center for Advanced Robotics at Queen Mary, or ARQ as we call it. And I'm actually not at Queen Mary, I'm actually at home. That's because of COVID-19 mainly. And I suppose that's why most of you are also at home, and that's why we have now an online workshop. So it is a workshop that is part of the conference RoboSoft 2021. And today we are focusing on soft interventional robots. And we want to explore the particular question, what's new since STIFLOP? And I will give a bit of an overview there on what this is about, why STIFLOP, what is it about soft robots for surgery and other medical applications. So our workshop will really look at current technology and particularly focusing on robot-assisted minimally invasive surgery. And what is now this paradigm shift that we are experiencing from rigid surgical tools to robotic systems that are highly redundant and soft in particular, and also capable of changing their structural stiffness to adapt to surgical needs. And then, of course, we will also look in the challenges that are still there to be overcome to really create useful soft robotic systems that can be used in medical surgical interventions. And we decided to add the subtitle, What's New Since STIFLOP, because that's when we started to look at this problem. And I think one can argue that we were the first to actually consider soft robotic devices for minimally invasive surgery. Yes, when we started in 2012, there were already others looking into soft robotics, but I think we were the first to consider that for this particular application. And so that's why we have this slightly provocative title there. Let's see where we are today, and I will definitely speak a bit more about where we came from in that project. Before I go there, so here's an overview of our workshop today. And so you can see we have quite a program. Very, very happy to see really these experts in the area joining us today and presenting on their newest work and their newest outcomes. So here's the overview, and so I put here on the left-hand side the time in the States. So it is Eastern Daytime. So 8:50 in the morning there. Good morning to America. Good afternoon to Europe, and good evening, good night to our colleagues from China. So yeah, really going across the continents, and for the US is, I suppose, quite good, and for the UK and the EU also quite okay, the times we have. However, we have also some colleagues from China, and so we suggested to them to, or we invited them to talk at the beginning, because I don't know whether they will be able to, attend the whole workshop until the very end. Anyway, so I give here a kind of separation. So first of all, looking at StiffFlop and the achievements there, but also the extensions and also very much the challenges that we have in that area. Then focus on new developments in soft and continuum robots for medical interventions. In the blue sections later, then we will go a bit further and look at surgical and medical robots and look at the implementation of those, but also at the modeling of soft robots and their environment. And finally, I hope that will be also very exciting. We have a roundtable discussion, and here we really want to summarize what happened today, and also see what we learned from there and what we can hopefully see for the future in that area. So here, just a slightly different view of the of today. So you should have that information also in an email that you have received. It's also available on the workshop website. And as you can see, we have really a tight program here. We have 4 2-hour blocks, and so each 2-hour block, or the first 3, are containing multiple presentations. And so we have for each presenter 20 minutes, and I would actually ask everyone to maybe stick to 18 minutes if it's possible. And then we hopefully will have one burning question. I want to allow one burning question after each presentation. But then we would like to continue with some breaks in between. And at the very end, really, come together again and discuss in more detail for the remaining 2 hours what we were talking today about, those soft interventional robots. I should also add that we will be recording everything. Actually, everything is automatically pushed onto YouTube. So yeah, I hope that is okay for everyone. Please do let me know if there's an issue with that. But yeah, I hope that is okay. One more quick thing. So we have Professor Kawai Kwok in the first block, and he might not be able to attend. So I would then probably ask Thrish to go a bit earlier, and we will have then a slightly extended break there. Yeah, but let's see, maybe he joins in the last minute. Okay, so without further view on the logistics, I would like to come to the origin of that workshop, so the project StiffFlop, and explore what we achieved there, and also look at the challenges that are still to be overcome. So really, the project was about looking between stiff and floppy, as I've said, so to create systems that could be stiff, but could also then change and become floppy. So really towards the creation of a fully integrated soft robot manipulation device for minimally invasive surgery. And from that, we created our proposal, and that was called StiffFlop, or in long, stiffness controllable, flexible and learnable manipulator for surgical operations. So an EU project coordinated by myself then at King's College, starting in 2012 and going to the end of 2015. And what were the objectives here? So the idea was to take inspiration from biology and to create systems, and we were particularly looking at the octopus there, systems that could morph from completely soft to entirely articulated. And then to really create systems that could be used for minimally invasive surgery. And there were a number of other things that we were looking into. So for example, distributed sensing, but also how could we now control such a system? And we were looking into intelligent control and learning-based approaches for this highly redundant manipulation device. And also looking not only into at the device itself, but how it would interact with the environment and what we can learn from that. And at the end, we saw then this system that could be used in minimally invasive surgery. So as I kind of indicated, that was a large-scale project, and I can only, thank all those who have contributed there. In total, we were 12 partners, and today I cannot unfortunately discuss DevLab in its entirety, so I will concentrate really on the soft robotics element. But yeah, so there was work done by IIT, for example, on navigation for soft robots in soft environments. We had control from the University of Surrey. University of Siegen was contributing to environment acquisition or signal image acquisition and providing improved control strategies. We were also looking into modeling, lots of input there from PIAP and the University of Surrey, but also very important haptic feedback for the user console, because we wanted to create a system that was integrated, so to speak, with the surgeon. So the surgeon should still have control, but automated functions should be there to improve the capabilities of the surgeons when carrying out their interventions. And so lots of input there from FRK, and it's great that Zbigniew is here today, and I think he will speak a bit more about the Robin Hart robot and other systems they have developed in the meantime. But there was also support from Technalia, and Shadow was instrumental for the integration of the whole system. So the idea really was to move away from systems like the Da Vinci robot, and here's just a quick video. You might have seen that beforehand. So a system made of rigid components, and that is an older system, but newer systems are based on the same principles. Also to mention here, very interesting work by colleague Guangzhong Yang, who will be also speaking later. At the time, he was working at Imperial College, developing the iSnake and also pushing the frontiers there. But our approach was to go beyond that. And here's another example of what was happening at the time. That was, you see how it shows that, developing the snake-like arm. Again, a very fascinating system. However, we wanted to really take one step further, move away from all rigid components in our systems that we were planning to develop as part of our StiffLab project. And our eyes were really very clearly on the octopus, taking inspiration from that fascinating element. And we had also a biologist on board, Benny Hochner from Jerusalem, advising us on the biological front. And so the idea was to really look at that problem from three directions. So we had our scientific experts from biology, we had loads of experts from the engineering side, but of course it was also very important to bring in the experts from medicine to ensure that what we develop is suitable for the problem that we were investigating. That is minimally invasive surgery, of course. And so Alberto is here today, and he will speak about the newest developments in that area later. But we had also input from Prakash Gupta from King's, in advising us on what is suitable for minimally invasive surgery. So our project was really about to create a system that could go beyond the standard laparoscopic tool, very rigid, made of metal materials. We wanted to create something that had the ability to bend, to elongate, to move inside the human body beyond obstacles, and to carry out then different types of tasks as required by minimally invasive surgery. And very, very key for us also was not to just create something that was soft, but also capable of changing its state from a soft one to a stiff one. Because on the one hand, soft, because we wanted to have it safe and we wanted to have it compliant to the environment, but also stiff is sometimes needed because forces need to be applied during operations. So for example, as I mentioned here, grasping, excising, or ablation. So we were focusing there on two main approaches. And as I said, the project really went beyond that, but I need to, I only have a short time here to, highlight the main points of this project with respect to focusing on the soft robotics side. So we were looking, as I said, into creating these soft robotic devices, but also interested then in different types of ways of stiffening, so changing from soft to stiff. So one was granular jamming, one stiffening approach, another one was tendon-based tensioning. And we applied these to two types of robots. We had the soft silicon robots, but we were also looking into inflatable fabric-based robots. So looking at those soft silicon robots, so from the beginning, we had in mind a modular approach, systems made from silicon rubber and to be pneumatically actuated. So I will skip now quickly through a number of systems that were being developed, and lots of input came here from SSSA in Pisa. And as you can see, we went through different stages that were the earlier systems, but already those proved to be very successful in being capable of bending, elongating, applying forces, and being also able to actually survive quite some strong force from the outside without breaking. So here we can now see one of those little robot fingers in action. So that was one of the segments, pneumatically actuated, 3 chambers in that segment, and you can see the joystick is moving there in the foreground, and that is controlling the air pressure going to to this small robot arm. And we were quite happy with that, but there were issues with the control. The system was very nonlinear, and we wanted to create, and we had to also add a membrane on the outside to contain everything. So the idea forward was then to create a system that had the reinforcement on the inside. So we created these silicon robot arms or segments. Here in gray, the silicon rubber, and in black, those chambers that can be inflated. And the black is actually a helical fiber on the outside to keep things together and to allow longitudinal extension within those chambers, which then leads to bending in different directions. And yeah, most of you have seen that video probably already. So here, an earlier prototype where we were testing the capabilities, and that is pneumatically actuated now, very soft, but still quite controllable, at least with a joystick. And as I always say, this is running in real time, so there's nothing is speeded up here. Good control, but also good speed can be achieved. Now, on the front of granular jamming, so here we developed approaches that would allow the integration of granules. And here it is just symbolized. So we have a structure that has a airtight membrane on the outside. And if we apply vacuum onto these granules, they come together, they they're pushed against each other, and the forces that are being applied will not will reduce the amount of bending. However, if we then allow air to come in, the whole structure becomes soft, and when we apply forces, bending is much more obvious. And that was then tested in a number of systems. Here we have a snake-like system, and now we apply the vacuum, and once you have applied it, the stiffness is increased. The posture that we have achieved there is kind of frozen. The system is stiffer now than beforehand. And we were integrating that into our system, and so we could now create robotic devices that could move around, but also be stiffer, or stiffness could be changed. We also developed a tendon-based stiffening approach, and that came actually, I will come back to that at a later point. We applied this approach also to our soft robotic structures, the ones I have presented beforehand. And the idea here is to integrate tendons into that structure, and these tendons can be pulled, so tension can be applied. And so the idea was to create an antagonistic stiffening system. On the one hand, the air pushes in the chambers, tries to extend the chambers, but on the other hand, there are tendons. I think it's Akil with the microphone still on. So if you could just switch off the microphone, that would be great. Thanks a lot. So these tendons pulling down against the pressure pushing up. So we have an antagonistic system that allowed us to control the stiffness of these devices. And we integrated that, as I said, into our silicon robots. And we could show that stiffening could be increased by this approach. So for example, here on the left-hand side, very obvious, without the stiffening by the tendons, we have a low stiffness, but higher forces can be achieved if we now apply the, pull the tendons down. And we moved forward on the developments, and we were able to miniaturize one of the big challenges, and we created the system that is here in the middle. And here we can see it moving about. So a 2-segment system with a camera integrated, and that was actually also then able to move through a standard trocar port into here a phantom of a human, and you see on the left-hand side in the inset the camera images coming back. We were actually able to move also into a human, so that was a cadaver study. Here on the left-hand side is actually Alberto, who will be speaking later, and supervising the experiments that we were carrying out. And the system showed to be successful in moving about in the internal cavities of this cadaver here. Just a quick extension from that work. So based on this idea of soft silicon robotic structures, we created a prosthetic hand, you can see here. Now I would like to also speak about our inflatable structures that we developed. And here again, we had this idea of applying an antagonistic approach. So you can see here a structure made of a fabric in black around the red void in the center. Air is pumped into this airtight fabric-based structure, and that allows us to deploy the structure. Tendons that are attached on the outside can be used for navigation, but can be also used to operate against the air pressure moving into the structure, and in this way change the stiffness. And also, I would like to highlight this particular one. These inflatable structures were actually also having another nice effect. You could, compact them very much, and then from a very small volume, expand into a very large volume. So very useful for the deployment of structures. And I would argue very much ahead of the competition. So these were already growing robots, and that was before immersion robots were being looked at as you probably know from Alison Okamura and Ethan Hawkes. And yeah, so once you have carried out your job, you can deflate it, take the system out again. You can use the tendons to steer the system in different directions. And we were, of course, keen to see whether that would also be suitable for use as a minimally invasive tool. And so here you can see how our system pushes through the trocar port and then can be moved around. Interesting, it can go through a trocar port that is actually smaller than the maximum diameter of the inflated structure. And we moved that further. And I think I've seen Agostino earlier here. So that was then turned into a system that could be used as an endoscope, so an inflatable endoscope. You see it here to contrast with existing systems that are rigid. And so that system could be then also inserted through a narrow opening and with a camera at the end used for inspection of the inside. So I have to hurry up now because I see I have only 3 minutes left. So we are also now looking at everting robots, so robots that unfold like a sleeve. And we have done some early work here to explore whether these could be used as an overtube in minimally invasive surgery. So you see here now a eversion robot pushing through one of these trocar ports. And we have extended that now, and you can see here that it's outside the medical field. We have now also created eversion robots that can be used, can evert, and at the same time bend in different directions. Just a minute on perception in soft robotics, also a very important topic of stiff flop. And so we were looking at optic-based approaches. We were using fiber optics, and they were used to measure bending or shape. We were using electroconductive yarn as well, as we can see here. And we also used the optics approach again to apply that to measure forces on structures. We were able to miniaturize that down to very small diameter, 3 millimeter diameter here. So 3-axis force sensor, 3 millimeter diameter. But one of the big problems were that these fibers were flexible, but not soft. So recent work focused on now creating light guides made from silicone rubber for integration with robotic structures. And I want to show here this example where we have this soft robot finger, which is now bending. And as you can see, for every movement the robot does, we can measure now the light intensity of that light guide and can use this to get an appreciation of the bending of that particular finger here. And we were able to also apply that to inflatable structures. And just very shortly, we're also looking into soft capacitive sensors, as we can see here. Now, I would like to just very quickly show the main challenges as I can see them coming out of stiff flop, but I think also still being at the forefront of soft robotics research. Stiffness controllability, accurate motion and position control, I think also still a challenge for these soft devices that we are developing. Creating soft sensors that can be integrated with a soft structure, navigation, and I would like to also add integration and miniaturization. And so I post these here now, and I think we will hear a lot from colleagues on their recent work, and we will see how this work relates to what we have here. Yeah, so I really have to highlight that this was not just a project by us then at King's, but really a number of people contributing. Yeah, just at the time photo of the team at King's. And yeah, that brings me to the end of my presentation. And that kind of, I don't know why this come here, yeah, but don't forget ICRA 2023. And so let's move forward. I think we don't have time for the burning question for me. Maybe you can ask me questions later.